Alright, so let's start exploring these phase transitions, okay? And to do that, what I'm going to start doing is drawing the isotherms of a van der Waals gas. So just remember, the van der Waals equation of state is like this, where we have the correction to the pressure due to the internal interactions, and we have the volumetric correction due to the finite size of the particles equals RT. So here, of course, as we have done, it is easy to get pressure as a function of volume by doing this. And now we can choose any fixed temperature we like, and we can plot P as a function of V, or the molar volume in this case, and we can make the Vp representation of those isotherms of a van der Waals gas like this. Okay, so let's put here the volume, or the molar volume, and here the pressure. So if my temperature is some large value, well, we will see that the isotherms are going to look a lot like the isotherms of an ideal gas. So that is, the pressure is a monotonically decreasing function of volume. And we can choose maybe a smaller temperature and we will see something similar. But if we keep reducing the temperature sufficiently, there will be a point where we will get something like this as an isotherm. Okay. So this isotherm is looking almost non-monotonic, and the corresponding temperature here, we're going to call it Tc for reasons will be clear later. Okay, so the temperatures above that, they are T larger than Tc. If we continue decreasing the temperature below Tc, what will happen is that we will have a non-monotonic curve, or of pressure as a function of volume, something like that. Okay, and okay, that is a strange thing. Mathematically, if you like, we can understand what is happening. Of course, if we just look at the van der Waals equation of state that we have there, we realize it's a third degree polynomial, no? So let's just multiply everything by b squared like this, and this is v minus b rt b squared. We make the multiplication here, and what we get is p v cube, and then what else? So it's minus pb, and then there would be the rt coming from the right hand side, v squared. And we have also the linear term AB, and we finally have minus AB equals 0. So this equation here is a cubic equation. You see, you have all the terms, all the orders, all the powers of B. And of course, we know that the solutions of these things are going to be three different solutions: V1, B2, and B3. So if we replace numbers, if we take some A and B for some specific gas, the constant, and we keep changing the temperatures, and we numerically solve this cubic equation, we will find that, for instance, at large temperatures, which are larger than this Tc temperature, or critical temperature, for any value of pressure, we will always have only one real solution of this. And the other two solutions, so let's say this one will be real, and the other two solutions will be complex, and they will be complex conjugate from one another. So this is why, for instance, when I'm sitting, say here, okay, if I am, well, I should have continued this a little bit further, but the point of, say, this isotherm here, at that pressure, it will only have one real value of the volume that corresponds to that pressure. Okay, and the other two volumes, if you like, that solve this equation up here are going to be complex, so they are not really physical, so I don't plot it. I don't have any problem. The problem comes when the temperature is lower than Tc, because then all three roots of this polynomial can be real. Okay, so this is what happens, for instance, in this last isotherm that I draw. I'm given the pressure, and I'm given the temperature, which in this case is smaller than Tc, and I have three apparently physically valid different values of the molar volume that correspond to that pressure and that temperature. Okay, and this is a big physical problem. Okay, because I told you before in the very beginning, and we know that if you have simple thermodynamic system, like a hydrostatic system, with only one component, you only have two thermodynamic degrees of freedom. You only have two free variables of state that you can select. And for instance, this could be pressure and temperature. And these ones are fixed along this isotherm. We are fixing the temperature, and we are also fixing what the pressure is. And this equation of state is telling me that there are three different compatible volumes, which doesn't make sense. Okay, so there is some physical problem here. If we keep thinking a little bit further about this, there is yet another problem with the van der Waals equation of state, because in the last chapter of liquefaction of gases, we learned that the isothermal compressibility, remember, was defined like this: partial derivative of B with respect to P at constant T, is always a positive quantity for stable thermodynamic states. Okay, so this means, if you want to rewrite it like this, partial derivative of B with respect to P at constant T, this equals 1 over V times beta T with a minus sign. Okay, I'm just inverting this, so putting it in the left hand side and bringing the isothermal compressibility to the right hand side. And this thing should be larger than 0. This thing is smaller than 0. Okay, because this guy here is positive, volume is always positive, and this is a minus sign. So what we know from the stability condition that we have derived in the previous lecture is that the pressure of any substance should be a monotonically decreasing function of its volume at constant temperature, that is along an isotherm. Okay, and this is certainly not the case for the van der Waals isotherms. We see that in this bit here there is an increase of pressure with volume, and it should be always decreasing. Okay, so that is a potential issue, and from what we know, this is telling us something about instability. Somehow the states of a van der Waals gas that are in this part of the isotherm should be unstable, because if they were stable, the curve should be monotonically decreasing. Now there are even bigger problems with the van der Waals equation of state, and if you keep reducing the temperature and plotting more if you keep plotting more isotherms, you will see that they look something like this. So still you get 3 possible different values of volume for every pressure, but I'm just calling your attention on what happens here at low molar volume. You see that the pressure is shooting up almost vertically. Okay, and this is telling us something about the system becoming almost incompressible. And in a gas, this is something weird, because a gas can be compressed. Okay, so this is somehow behaving more like a liquid than a gas. So this is another key of what is really happening in this part of the graph, that the system becomes incompressible. And the final issue with the van der Waals isotherms is that really they don't work at too low temperature. So if temperature is really too low, you will altogether have negative pressures like this, which is completely unphysical. So we know that, okay, on the one hand, this negative pressure issue is worrying. Okay, so it just means van der Waals equation doesn't work at very low temperatures, but at not so low temperatures we still have positive pressure, and we do have some concerning things as well, like instability and incompressibility at low molar volume. So to try to resolve what's happening and whether we should ditch a van der Waals equation for good or not, what is useful to do always is to go and look what happens to a real gas. Okay, so now this is not say a phenomenological equation of state that I'm using to draw the isotherms. I'm actually going to the lab and take a gas, and I put it in a cylinder with let's draw it like this. So I put it in a cylinder, and the walls of this cylinder are going to be, in this case, diathermal, and outside the temperature is T. So the temperature inside is also fixed at T. We have a piston here that we can move to change the volume available to the gas. And simultaneously here I'm going to make a drawing, the VP representation once again of what is happening in this system, okay? So here I have volume and here I have pressure. So imagine I have a gas here. Let's represent it like a bunch of little dots like this, okay? In a moment you will see why. And what I'm going to do, so imagine this, I'm starting in point A, so this is state A, I'm somewhere here, and what happens when I compress this piston, I push it down a little bit, is that the pressure starts growing, okay? It starts growing monotonically, like that, okay? So then, at some point, I will see, and this is something that will happen, I will see this, that there will be some small droplets appearing in the gas. And these droplets, of course, they're going to fall by gravity to the bottom of the container, and they will form a liquid phase. Okay, so at this point, the pressure in my system is PB. And if I go look at my system here, I see that the gas here and the liquid, which is underneath, are both at the same pressure, PB. Okay, so this is known as the saturation pressure. Let's say PB is saturation pressure. So we have a liquid which is in thermodynamic equilibrium with a gas in the same state. So at the same temperature and the same saturation pressure. The only thing is that because the liquid is a liquid, so of course the molar volume of the liquid is going to be much lower. Okay, so while this point here in the graph represents what the gas is doing, so this represents this part of the system, this other point here represents what happens to the liquid. Okay, it is at the right pressure, which we are going to call this point here F for reasons that are going to become clear later, and this this pressure is the same in both cases, but the molar volume is different. Okay, so this is BF and this is BB. And of course the temperature is the same. If I continue compressing my piston more and more, what happens is that more of the gas is going to condense and fall into the bottom of the container. And more and more and more and more, until there comes a point in which all of the gas has become liquid. Okay, so when this happens, if you try to compress this a little bit further, you will find a lot more resistance. So it's a lot more difficult to compress a liquid than it is to compress a gas, and you will see that there will be a very, very sharp raise in the pressure because the system has become almost incompressible. And what you are left with is something like this. Okay, when this horizontal line means nothing but, okay, you know, part of the system is described by this state here, and part of the system is described by that state over there. So what really happens to a real gas when the temperature is low enough is that there will be a phase transition. The gas will go from gas to liquid, okay? And this is something that the van der Waals equation of state misses. And the reason why it misses this point is because it starts from the assumption that the most stable state of a system is always going to be an homogeneous state. And we have just seen here in experiment, if you like, that the thermodynamic system is more stable, at some point it becomes more stable, if it splits into two phases that coexist in equilibrium with one another. Okay, so this inhomogeneity is what gives rise to this flat part of the isotherm here. Okay. So what the van der Waals isotherm would predict for this system would be slightly different. I will actually redraw this a little bit better because drawing is not going to look nice like this. Okay, so what the van der Waals isotherm tells us for this substance and for these parameters will always going to be, look, let me try to make the drawing accurate, something like this. Okay, so while I start in state A, okay, both van der Waals equation and me we agree up to B, and then what I see in reality is this D, we go to this point D, E, F, and that's it. But what the Van der Waals equation of state would predict is that we go from A to B, and then instead of going to C, which is not even considered in this equation, we go to some other state, H up here, and then we continue, we go to D, and we go down to G, and then we go to F, and then we continue going up, okay? So at reality, let me just write reality, or real, would be A, B, C, D, E, F. And what the Van der Waals equation predicts is A, B, H, D, G, F. Okay? And we know that this bit here, which is different, yes, this G, D, H, is really the bit that is telling me that it's unstable. So it's the bit where the pressure is a monotonically increasing function, or is it an increasing function of volume, which it can be if the system is stable. These states in red here, it doesn't mean that they don't exist or you cannot realize it. Okay, so imagine that you repeat this experiment that I said here, and you start compressing the gas, but you are doing it in extremely clean conditions. Okay, so you're really extremely careful, and maybe you're able to see that the pressure raises in a way that you follow the Van der Waals isotherm for a while. The thing is, any small perturbation, if you shake the system a little bit, or if there are any dust particles somewhere, there will be nucleation, and the gas will condensate and it will drop to the bottom of the container, and you will suddenly fall into this situation where you have gas and liquid in thermal equilibrium. So what really happens to these red states here is that, yes, they are not impossible, and it's not that they don't exist, they are just not the most stable choice for the system. And if the system has a chance to decide, it will decide to go to the more stable split phase situation, in which you have liquid and which you have gas in a non-homogeneous situation. And the same thing happens with these states down here. If you have a liquid and you start expanding the liquid extremely slowly and carefully, you may find that the molar volume of the liquid can be in these values here with a lower pressure than you actually find in reality. Okay, and of course, again, this is unstable, and any perturbation will bring the system to its truly stable situation, in which it splits into two phases. Okay, so this line here, okay, the line at the saturation pressure that describes the process in which the system is being converted from gas to liquid phase, is known as Maxwell line. And what we're going to do next in the next video is to learn how we calculate this line here and how we get the saturation pressure out.